everyone, and welcome to part 2 of the lecture video on alkene addition reactions. Okay, so just as a reminder, if you have addition 3 and beyond, this will be chapter 8, and if you have addition 1 and 2, this would be chapter 9. All right, so we mentioned that there are many reactions covered in this chapter, and part 2 will cover items number 3, 4, and 5 from this list. Acid catalyzed hydration and oxymercuration demercuration are actually two different reactions. However, they sometimes produce the same product and have slightly different considerations, so they're grouped together. And then hydroboration oxidation will be covered today, as well as hydrogenation. Let's start with acid catalyzed hydration. So a hydration reaction is when water is added across the double bond. Water is H2O, but that is split up into hydrogen and OH. So in this case, both an H and an OH are added across the double bond. Acid catalyzed hydration does follow Markovnikov regioselectivity, meaning that the hydrogen gets added to the less substituted carbon, and the OH group gets added to the more substituted carbon. Typically, we do need an acid catalyst, and typically sulfuric acid is used as the acid catalyst. There's a good reason for that. Sulfuric acid will have water in it, and water is needed for the reaction, but it also produces protons without a conjugate base that can interfere. If we had used, for example, HCl as the acid, then once the proton has been transferred, we have chloride, which can act as a nucleophile. Sulfuric acid's conjugate base is non-nucleophilic, which is great because we want water to be the nucleophile, not the conjugate base of the acid. And so we just need the acid to give us some protons. And this reaction only needs a catalytic amount of acid because it gets used and regenerated in the mechanism. Let's look at some studies that have been done on different substrates in this acid catalyzed hydration reaction. What we see is that the OH will get added to the more substituted carbon, and the more substituted that carbon is, the faster the reaction. This sort of data is consistent with a mechanism involving a carbocation intermediate, because more substituted carbons with a positive charge are more stable and therefore expected to react faster. Let's go ahead and now look at the acid catalyzed hydration mechanism. The mechanism starts off very similarly to hydrohalogenation, which we covered in the last class. The first step is proton transfer, where the acid is donating a proton to the alkene substrate. So in this case, the pi bond is acting as a base and doing a proton transfer, picking up an acid, in this case from hydronium ion. Recall that the proton will selectively go to the the less substituted carbon, such that the more substituted carbocation will form. So the carbocation intermediate will occur regioselectively to form the most substituted and most stable carbocation, which in this case is a tertiary carbocation. After the carbocation is formed, then there can be a nucleophilic attack. Recall that water is going to be the nucleophile in the acid catalyzed hydration mechanism. Water is considered a weak nucleophile. That's what we learned when we were studying SN1 reactions. However, it is still a strong enough nucleophile to attack a highly electrophilic positive charge. The difference now with hydrohalogenation, which we studied last time, and acid catalyzed hydration is that with hydrohalogenation, after the proton transfer to form the carbocation, the halogen attacked the carbocation and the mechanism was done. In this case, water is attacking as the nucleophile, and an oxonium ion is produced. That's an oxygen with a positive charge. So we're still not done with the mechanism because oxonium ions are charged and are not as stable as neutral species. Therefore, a final proton transfer with water now acting as a base will occur to generate the neutral alcohol product. Acid catalyzed hydration is a reversible process. You may have learned that we actually already learned the reverse process in the elimination chapter. Recall that if we take an alcohol substrate and treat it with concentrated acid, it will dehydrate to form an alkene product, which is the product of an elimination reaction, and also water. So this acid catalyzed hydration is the reverse of that elimination process and occurs when a dilute solution of sulfuric acid is used. Dilute solutions of sulfuric acid have more water, and water is a reactant in the reaction going from left to right. Water is a product in the elimination. So a concentrated sulfuric acid would drive the reaction to form more water so that the acid solution becomes more dilute. So we're able to play around with the concentration of the acid used to exploit the Chatelier's principle to control the equilibrium in this process. Let's talk now about the stereochemistry of the acid catalyzed hydration mechanism. So the stereochemistry is analogous to hydrohalogenation, which we talked about again last time, and also for the same reasons. Recall that a carbocation is formed in both reactions, which will get attacked by a nucleophile, which is either a halide ion, as in the hydrohalogenation reaction, or water in the hydration reaction. Either way, a carbocation intermediate is formed in both mechanisms. And as a result, that carbon is sp2 and trigonal planar, and the nucleophile, regardless of which nucleophile it is, can approach that empty p orbital from either face, leading to a mixture of enantiomers. So if you're forming a chiral center, a racemic mixture will be formed. Let's talk about a very similar reaction. It's similar in some ways. The similarity is that we are trying to get the same sort of product. We're trying to get a hydration product that follows Markovnikov regioselectivity, meaning that the hydrogen gets added to the less substituted carbon, and the OH group gets added to the more substituted carbon. So you can see that this is essentially a Markovnikov hydration. However, this is an entirely different reaction with different reagents occurring through a different mechanism. And you might ask yourself, why would we learn two different reactions that do the same thing? And the answer is they don't do exactly the same thing. On some substrates, which a carbocation would not lead to rearrangement, the product would be the same. However, oxymercuration, demercuration as a reaction has some advantages. And the advantages are that it does not go through a true carbocation intermediate, and therefore there will be no rearrangement. And remember that rearrangements lead to mixtures of products, which organic chemists want to avoid. So oxymercuration, demercuration, it still does Markovnikov addition of hydrogen and OH across a double bond. But the advantage, again, is that no rearrangements can occur with this particular mechanism. So if you're dealing with a substrate that would go through a carbocation intermediate that would rearrange, that would be a prime candidate to do oxymercuration, demercuration instead of acid catalyzed hydration. The disadvantage, of course, is that the reagents are not as readily available and are much more expensive. We're going to use mercuric acetate in this reaction, which is obviously a lot more expensive than just using a solution of sulfuric acid in water. So oxymercuration, demercuration, is a two-step process. And the first step uses mercuric acetate and water. Mercuric acetate is the mercury ion itself will act as a Lewis acid in this reaction, which will replace the need to use a Bronsted-Lowry acid, such as sulfuric acid. So mercuric acetate has a mercury, which is metal, and it has two acetates attached to it. And when we're dealing with metals, the groups attached to metals are often called ligands. So those ligands can sort of associate with the metal or disassociate. So they sort of do a nucleophilic attack followed by loss of a leaving group. And that's in an equilibrium process. So if we lose one of the acetates with loss of a leaving group, then we end up with this positively charged mercuric cation. Because it's positively charged, it's electrophilic, and so it can act as a Lewis acid, which can take the place of, again, a proton, which is a Bronsted-Lowry acid. So just like pi bonds do a proton transfer, where they act as a base and they pick up a proton from a Bronsted-Lowry acid, such as sulfuric acid, pi bonds can also act as a nucleophile, or you can think of it as a Lewis base attacking a Lewis acid. So they attack the electrophilic mercuric cation, and herein lies the difference. When the pi bond acted as a base to pick up a proton, a true carbocation is formed. True carbocations can lead to rearrangement in some cases. Whereas when the pi bond acts as a Lewis base and attacks the mercuric cation, a true carbocation is not what is formed. Instead, it's a carbon that's positively charged, but is stabilized by electrons on the mercury. So sometimes people draw this three-membered ring, which is called a mercurinium ion. But because the electrons on the mercury are helping to stabilize the positive charge, there's less positive charge on this carbon, and it is not subject to rearrangement. Once the mercurinium ion is formed, which, by the way, this is not a full bond, but kind of a partial bond, where the positive charge is shared between the carbon and the mercury. This is set up for nucleophilic attack. The nucleophile that will attack in this oxymercuration-demercuration reaction is water. Water will be the nucleophile that attacks. And you might ask yourself, why is water attacking the more substituted carbon instead of the less substituted carbon? Because this appears to be an SN2-like reaction, where the nucleophile comes in from the back and the leaving group leaves. And even though this is SN2-like, it's actually attacking the more sterically hindered carbon, not the less sterically hindered carbon like you would normally see in most SN2 reactions. The reason why is, again, that this bond is weakened. And even though there isn't a full positive charge on this carbon, there is a partial positive charge. So some of that positive character is on the carbon and some of it is on the mercury. So this bond is weakened, and it's weakened more towards the carbon that can handle the positive charge better or can stabilize it better, which is the tertiary carbon. So even though we draw this as an SN2 mechanism, it's kind of more what we call in between SN2 and SN1, where there's no true carbocation being formed, but there is still backside attack. And then once the nucleophile has been attacked and deprotonated, you'll have your OH group on this carbon. And then the mercuric acetate on the less substituted carbon is replaced with a hydrogen in the second step, which the reagent for that is sodium borohydride. So you can see here the way that the reagents are written over the arrow for the oxymercuration-demercuration reaction. The first step is mercuric acetate and water, and the second step is sodium borohydride. Remember that these two reactions, acid catalyzed hydration and oxymercuration demercuration, do a very similar reaction. Overall, they are doing Markovnikov hydration. However, the difference is that with acid catalyzed hydration, with some substrates where rearrangement is possible, will often lead to a mixture of products that occur from the reaction either going through rearrangement or the nucleophile attacking prior to rearrangement. With oxymercuration demercuration, we're able to get Markovnikov hydration without rearrangement. So no shift is occurring, and that means we only get one product, which is an advantage for synthetic chemists. Of course, if we were dealing with a substrate where we don't have to worry about rearrangement, it would be better to use acid catalyzed hydration because that's a much cheaper reaction, only having to use acid as the reagent. We don't want to have to use mercuric acetate and sodium borohydride. Those reagents are much more expensive. However, if we're dealing with a substrate such as these two, where we would have to be concerned with rearrangement, we would want to use this reaction, even though the reagents are more expensive, in order to avoid getting a mixture of products. Let's move on to another reaction called hydroboration oxidation. Hydroboration oxidation is also a hydration reaction, similar to the last two reactions we were talking about. But in this case, we get anti-Markovnikov regioselectivity. So we're still adding hydrogen and OH across the double bond, but in this case, the OH group gets added to the less substituted carbon. This is great for organic chemists to have an alternative to get the opposite regioselectivity in case that is what is desired. The reagents for hydroboration oxidation start with borane stabilized in THF. So THF stands for tetrahydrofuran, and it's an organic solvent. But typically you'll see it as BH3.THF, and this just means that it's stabilized in this solvent. And I'll explain what that means. And then there's a second reaction or step, which involves adding hydrogen peroxide and sodium hydroxide. So these reagents are added sequentially. First, the borane that's stabilized is added, followed by the addition of sodium hydroxide and hydrogen peroxide. The 1,2 means that these are not all mixed in the same pot at the same time, but instead this is like two individual reactions that have been sequenced to produce the product in one step. There is some important stereoselectivity in the hydroboration oxidation reaction. So remember that in hydroboration oxidation, we are getting H and OH added across the double bond. And that does occur through anti-Markovnikov regioselectivity, which is why the OH got added to the less substituted carbon. Stereoselectivity refers to the reaction that can produce potential stereoisomers, and some being selective over others. So the stereoselectivity is that syn addition is occurring. What is syn addition? Syn addition means that both the hydrogen that's getting added and the OH group that's getting added are added to the same side of the double bond. So if they're both added from the top, then they would both be on a wedge. If they both get added from the other side of the double bond, think of it as coming in from the back side, then they would both be on a dash. Either way, right, they are always going to be added from the same side of the double bond. Anti-selectivity is not observed in this reaction. So if you have a methyl group here and the hydrogen gets added from the top, that will push this methyl group back, right? Because this became a chiral center, we need to make sure to put something on a dash and something on a wedge. Let's talk about the mechanism and what's happening in the hydroboration oxidation reaction. The first reagent is BH3, borane. Borane is a boron atom with 3 hydrogens attached, and it's trigonal planar with an empty p orbital, just like a carbocation. Although it doesn't have a formal positive charge, based on the way that formal charge is calculated, it still has an empty p orbital, and the boron still lacks an octet, similar to the carbon in a carbocation. And as a result, that boron is electrophilic, just like the carbon in a carbocation that's positively charged is electrophilic, which means that nucleophiles can come and attack it by donating electrons into that empty p orbital. Because the boron does not have an octet, it is reactive and it needs to be stabilized. So it is typically stabilized in a solvent, such as an ether solvent like THF, which again stands for tetrahydrofuran. Ethers are perfect to stabilize borane because the oxygen has a lone pair. Actually, it has 2 lone pairs, but it can use one of those lone pairs to help donate electron density into that p orbital, helping to stabilize it. This is a reversible process. The THF can do a nucleophilic attack to form what we call this Lewis acid-base complex, and it can also reverse or do loss of a leaving group to go right back to THF and borane separately. So the complex is written as BH3.THF, and again, it's just stabilized borane. This is not an important part of the reaction mechanism. It is not reacting with the alkene. This is just an organic solvent that helps to stabilize the boron. Think of like when you learned, actually, never mind. I'll just move on from that because you haven't learned that yet. Okay, so hydroboration oxidation mechanism. So remember we said that BH3 is stabilized with THF, but that the THF can coordinate to form the complex and then also go back to regular borane and THF. So this is just regular borane, and it can be attacked by the pi bond in an alkene. Remember I said that the boron is electrophilic. Well, we know that pi bonds are basic and nucleophilic. So if it acts as a nucleophile, it can do an attack on the boron, which can lead to triggering a hydride shift. So as soon as these pi electrons start associating with the boron, that would leave a positive charge developing at this tertiary carbon. And then because the boron is taking on a negative charge with this extra electron density, it can lose 2 electrons in the form of a hydride shift. So that has occurred to form this alkyl borane intermediate. And then this alkyl borane intermediate can react with 2 more alkenes in order to get 3 alkyl groups attached instead of 0. So it starts off with 3 hydrogens attached, and after this process occurs 3 times, it ends up with 3 alkyl groups. And the alkyl groups are all this, in this particular example, they're this isobutyl group. So sometimes the mechanism is drawn sort of with the nucleophilic attack happening first, followed by the hydride shift, or sometimes it's just drawn where those steps are happening sequentially, where we have the pi electrons starting to attack and form a bond between the less substituted carbon and the boron, and then the hydride shift happening simultaneously. So sterics also influence the regioselectivity. Notice that the boron gets added to the less substituted carbon, and the hydrogen ends up adding to the more substituted carbon. This happens in part because of the stability of the transition state. When there's less steric hindrance versus flipping the borane around and having the boron add to the more substituted carbon, and thereby experiencing a more crowded, sterically hindered situation. So this helps explain the regioselectivity. So the hydrogen gets added to the more substituted carbon, the boron gets added to the less substituted carbon, and then the carbon-boron bond is eventually replaced with an OH group. And so we end up with anti-Markovnikov regioselectivity. So this is what's happening in the second step of the hydroboration oxidation mechanism. It's a lot of steps, but I'm going to walk you through it just so that you understand what's happening. You're not going to be expected to draw all of this out though. So remember that in the second step, we're treating the alkyl borane with both hydrogen peroxide and sodium hydroxide. Well, sodium hydroxide can deprotonate hydrogen peroxide, making the peroxide anion. This oxygen is nucleophilic, and so it can attack the boron, leading to a boron that's negatively charged, which can then trigger a rearrangement. In this case, there'll be an alkyde shift. This was a methyl group, we would call it a methide shift, but any group can migrate, so it can be any R group. So we can just kind of generically call that an alkyde shift or a type of rearrangement. And hydroxide will act as a leaving group in that case. What we've essentially done now is inserted an oxygen between the carbon and boron. That can happen 2 more times to get the trialkoxyborane intermediate. So that process happens where hydrogen peroxide anion attacks again, which creates another rearrangement, inserting a second oxygen between boron and carbon, and that can happen a 3rd time. At this point, hydroxide is still in solution and can still attack the boron, which is electrophilic, leading to a boron that's negatively charged, which can lose a group. So we can start kicking out these alkoxy groups, which can eventually be protonated with water to give us the alcohol product that we see in the hydroboration oxidation reaction. So remember, with hydroboration oxidation, you need to remember how to draw the reagents for that. And you need to look at this and know exactly what's happening. So I want you to look at these reagents and go, hydroboration oxidation, anti-Markovnikov hydration reaction. The hydrogen is going to go on the more substituted carbon, and the OH group will be placed on the less substituted carbon. Center, a mixture of enantiomers is formed, and you're going to find that that's going to be the same in all reactions. Whenever one chiral center is formed, a racemic mixture of enantiomers is always formed. And that's because there's no selectivity for the reagents attacking on one side of the pi bond or on the other side of the pi bond, right? And those pi bonds are planar. That attack can occur with equal probability, leading to both enantiomers. However, when you form more than one chiral center, then you can start talking about whether or not a reaction has syn selectivity, anti-selectivity, or no selectivity at all. So in reactions previously where we said there was no selectivity, that means if you form 2 chiral centers, you would form a mixture of all 4 possible stereoisomers. So reactions which are syn selective only form 2 products when 2 chiral centers are formed. Again, any of these reactions, if only 1 chiral center is formed, you will always get a racemic mixture of the 2 enantiomers. However, therein comes a difference when 2 chiral centers are formed. When 2 chiral centers are formed, you need to ask yourself, is the reaction that I'm dealing with syn selective, anti-selective, or have no selectivity? If it doesn't have syn or anti-selectivity, and there's 2 chiral centers formed, 4 stereoisomers will result. But if it is syn selective, only 2 stereoisomers result when 2 chiral centers are formed. And those are specifically adding those 2 groups on the same side of the pi bond. So remember, in hydroboration oxidation, we're adding H and OH across the double bond. It does go through anti-Markovnikov regioselectivity, But stereoselectively, that H and OH get added to the same side of the pi bond, which is why you see the hydrogen and the OH are always going to be either both back or both coming out of the plane. Let's do some practice. Go ahead and pause the video and try to answer this practice problem. The question is, predict the products of the following reaction. And then, what if that same substrate was treated with catalytic sulfuric acid or mercuric acetate and water followed by sodium borohydride? What would be the difference in the products, and what is the relationship between those products? All right, let's go ahead and go over the problem. So we have hydroboration oxidation. So recall, the first thing you want to ask yourself is, given these conditions, what is getting added across the double bond? And the answer is H and OH, because this is a hydration, and it goes anti-Markovnikov. So that means that the hydrogen will go on the more substituted carbon, and the OH will go on the less substituted carbon. And when that happens, both of these carbons are going to become chiral centers. So when you're going to form two new chiral centers, remember that this reaction exhibits syn selectivity. So both the H and the OH get added from the same side. So if we're sketching that out, the first thing we want to do is just go ahead and add this methyl in, because that's not going to get touched in this reaction. And then we're going to add H and OH, and the OH will go here. So let's say that the OH goes and adds from the top. That means that the hydrogen here also got added from the top, which pushes the methyl at that carbon down. You can also draw in the up hydrogen here, but you don't need to. And then we also have the stereoisomer, where both the OH and the H get added from the bottom. So if the hydrogen gets added from the bottom here, that pushes the methyl up. And what is the relationship between these products? Right? This one has the same stereocenter, opposite and opposite. So these are diastereomers. Let's look at what would have resulted if the same substrate was treated with Markovnikov hydration conditions. I'm going to go ahead and draw the same substrate in. And then I'm going to draw two different reaction conditions. And you'll see why I'm doing it this way in a minute. The reason why is because this is going to give me Markovnikov selectivity. So my H will go here, my OH will go here, and this will not become a chiral center. And this will go through a tertiary carbocation, which will not rearrange. And since there's no rearrangement, then I don't have to worry about rearrangement, in which case the product in either case of the two different sets of conditions will be the same. So either we will do catalytic H2SO4, which of course means that there's also water present, or oxymercuration demercuration, you should be able to eventually draw out these conditions, right? Knowing the reaction that you want to use. And then Again, we're going to ask ourselves, what's getting added across the double bond? Well, it's still a hydration, so H and OH. This one goes through Markovnikov regioselectivity, and there is no stereoselectivity. Right? So in either one of these cases, there's no stereoselectivity. I should write this. Okay, so drawing that out, you're going to have 5-membered ring here. This will not be touched. And then with Markovnikov, we're going to end up with the OH on the more substituted carbon and the hydrogen here. So this is just going to become a CH2, and then there'll be an OH here, and this will make this a chiral center. So you're going to get both the OH added from the bottom and the OH added from the top. And if you ask yourself, what is the relationship between these? Again, they have one chiral center that's the same and one that's opposite. So these are still related as diastereomers. Right? So no rearrangement. So both additions give the same products. Okay. Let's go back to the slides. So next we're going to talk about catalytic hydrogenation. So hydrogenation is a reaction where we're adding 2 hydrogens across a double bond. It does require a metal catalyst, and some common catalysts are platinum, palladium, and even some other catalysts like ruthenium or different metals can be used. The alkene is converted to the corresponding alkane by reduction of this pi bond. Later, probably in the second semester, you'll learn about calculating oxidation state for different carbons. And so you'll understand why I'm calling this a conversion of a double bond to a single bond a reduction. But for now, you can just take my word for it. So again, the reagents are H2, and both carbons are getting a bond to hydrogen and a metal catalyst. So essentially, we're adding a proton on one side and a hydride on the other side, because we do need to add those electrons in as well. This reaction is obviously not regioselective, because when you're adding the same group across the double bond, that it doesn't matter which carbon gets which, because they're both getting a hydrogen regardless. So regioselectivity in these alkene addition reactions is only considered when you're adding 2 different groups across the double bond. But this reaction is stereospecific. Only syn addition is observed with hydrogenation, which means that both hydrogens are added to the same face of the double bond. In this case, they've been added both to the back. So we have hydrogens on dashes at both carbons. And in this case, both hydrogens have been added to the top face. And so both hydrogens here would be going out at you or on wedges. Anti-addition is not observed in this particular reaction. So the metal catalyst, what does it do? Well, essentially it provides an alternate pathway with a lower activation energy that can allow the reaction to occur more feasibly. So the alternate pathway is essentially the metal is acting sort of as a matchmaker. Not only does it coordinate to pi bonds, but the metal surface itself, which by the way is still drawn as a solid because the metal does not dissolve in the solvent. So it is just floating around in tiny particles in the solvent, so it's still a metal surface. It coordinates to pi bonds, and it also absorbs hydrogen gas on its surface. And as a result, only one face of this pi bond is being exposed to the metal, and that's the face that will get the hydrogen atom. So the hydrogen atoms get added to the same face of the double bond because it's being essentially added across the surface of the metal. But be careful, because when you start with a substrate like this and you add the hydrogens to the same side, you don't actually get a mixture of enantiomers in this case. These are the same thing because this is a meso compound. So there's an internal plane of symmetry, right? Meaning that this is not a chiral compound. You can also think of it as take this and flip it over, and you'll be able to superimpose it on the other one. So sometimes you're only going to get one product if it's a meso compound, or if there's two different chiral centers, then you would get a mixture of enantiomers that only occur through syn addition. Okay, let's talk about predicting the products of addition reactions. So I've kind of been demonstrating the process for you as we've done practice problems, both last class and this class. But the first question you want to ask yourself when you're trying to predict products is look at the reagents and ask yourself, what is getting added across the double bond? So answers might be two hydrogens, a hydrogen and an OH group, a hydrogen and a halogen. And there'll be some more examples as well as we study more reactions. So first ask yourself, what's getting added across the double bond? If it's the same groups, then you don't need to consider regioselectivity. But if they're different groups, then you need to ask yourself, okay, which carbon, either the more substituted or the less substituted, is going to get which group? A lot of times one of the group is hydrogen and the other group is a larger group. And in that case, we say that the reaction is either Markovnikov or anti-Markovnikov in terms of its regioselectivity. So if the larger group goes on the more substituted carbon, then it's Markovnikov regioselective. And if it goes on the less substituted carbon, then it's anti-Markovnikov regioselective. So those are important things to note, right? If you're not adding the same group, which carbon gets which group? And then stereospecificity. Some reactions are labeled syn-selective or anti-selective. We haven't seen any anti-selective reactions yet, but we will in the next class. However, it's important to note if certain reactions are syn or anti-selective, because that comes into play when two stereocenters are formed, and we want to make sure that we're drawing the correct selectivity. If only one stereocenter is being formed, then it's always a racemic mixture, no matter which reaction that you're discussing in this chapter. So it's really important that you do some minor reagent memorization and understand the mechanisms, like why is it Markovnikov or anti-Markovnikov? What sort of mechanism? Is it going through a carbocation intermediate? Is it going through a radical intermediate? Those sorts of things really help you to remember and not just rely entirely on memory. And the more familiar you are with these mechanisms, the easier it will be to remember the selectivity in the reaction. Because sometimes you may forget if you rely on entirely memorization, but if you understand the mechanisms and you kind of understand the reason behind the result. So to set up a synthesis, ask yourself, can I do this in one step or more than one step? Reactions that can be done in one step, for example, are addition reactions, where we're starting from an alkene and adding different groups across the double bond. Substitution reactions and also elimination reactions. Those are all reactions that we've learned so far. So if it's a simple elimination or substitution or addition reaction, those are just one-step processes that you've been learning about. Let's look at this example. Do we need one step or more than one step to convert this alkene to this alcohol? Notice that we are essentially doing an addition reaction. We are adding two groups across the double bond. We need to add a group to this carbon and add a group to this carbon. A hydrogen gets added on this carbon, and an OH gets added on the more substituted carbon. So overall, this is a hydration because one carbon is getting hydrogen, the other carbon is getting OH group, which together is H2O. And this undergoes Markovnikov regioselectivity because the OH group is getting added at the more substituted carbon. So ask yourself, which reaction conditions do I know that give me Markovnikov hydration reaction? There's two. You can either do acid catalyzed hydration or oxymercuration demercuration. However, in this case, if we did acid catalyzed hydration, we would end up with a tertiary carbocation, which would not rearrange. So we don't have to concern ourselves with rearrangement, and we can use the cheaper reaction of acid catalyzed hydration. And we don't need to do oxymercuration demercuration. We could do it, but most people would not because it's simply more expensive. So you would not want to do that if you did not have to. Let's go ahead and add in the conditions for that. We want to do acid catalyzed hydration. We can just write catalytic H2SO4. Sometimes people also just write H2SO4 with brackets around it, which also means catalytic H2SO4. And that will always be an aqueous solution. So whether or not water is mentioned, we know that it is present in the reaction. Let's look at another example. We are converting one alcohol into a different alcohol. So the OH group has migrated from this tertiary carbon to this primary carbon. So this is not a simple addition reaction because addition reactions always start with an alkene. It is not a substitution because the group is the same, it's just changed positions. And it's not an elimination because an alkene is always the product of an elimination. So this is not a one-step transformation. We need to do more than one process combined. Whenever a functional group has moved positions, you can do a series of additions and eliminations. In the case where this functional group is already there, we can eliminate it first, followed by add it in a different position. Because we want the OH group to end up on this carbon, we want to make sure our alkene gets formed between these two carbons. That way we can do an addition reaction and make sure the OH ends up on one of those two carbons. So overall, we want to do an elimination specific to getting this alkene, which if you look, this is going to be the Hoffman alkene. And then we're going to do an addition where we're going to do a hydration, and it's going to go anti-Markovnikov because the OH group is going to add to the less substituted carbon. So in terms of how are we going to actually accomplish these two steps, what reagents do we need? So for the elimination, we need to recognize that OH is not a good leaving group for an elimination reaction. So we need to convert it to a good leaving group and get it to do an elimination reaction. Recall that if we use acid, that will allow the reaction to undergo E1, and we'll always get the Zaitsev product as the major product. But in this case, we're going for the Hoffman product. The only way to get the Hoffman product is to do an E2 reaction. And an E2 reaction utilizes a strong base, which is not compatible with a strong acid. Therefore, we will not use acid to make this a good leaving group. Instead, we will convert it to a tosyl group using tosyl chloride and pyridine. This is another way of accomplishing the formation of a good leaving group without using acid. Next, we can use a bulky strong base to do E2 and give us the desired Hoffman regioselectivity. From there, we need to do an addition reaction. And specifically, we want to do anti-Markovnikov hydration. It's a hydration because we're adding H and OH across the double bond. And it's anti-Markovnikov because of where the larger group is getting placed specifically on the less substituted carbon. So we want to remember that if I want to do anti-Markovnikov hydration, I need to do hydroboration oxidation. That's the way your brain needs to think in order to be able to do these sorts of problems. So you need to remember what is the relevant regioselectivity? What is, if any, relevant stereoselectivity? We did not have to worry about stereoselectivity in this case, even though this reaction is known to be syn selective. The reason we did not have to worry about it is because we did not form any stereocenters. So if you're not forming any stereocenters, you don't need to consider stereoselectivity. If we had formed one stereocenter, we would have formed a racemic mixture. If we had formed two stereocenters, we would have made sure to draw the two products that correspond to syn selectivity. Specifically, the hydrogen in the OH group should have gotten added across the pi bond from the same face, either both up or both down. I encourage you guys to practice lots of problems from the book.